It's a great pleasure to welcome Qian here today. She did her PhD in Urbana-Champaign, University of Illinois, back in 12, not so long ago. And since then, she's been a Miller postdoctoral fellow in Berkeley with Paul Alivisatos. And we look very much forward to hearing you today. Please.
Thank you so much for the introduction. I'm Qian Chen from UC Berkeley. Today, I'd like to share with you some insights I learned from dynamics. Dynamics is everywhere. For example, this winter, many of us are enjoying the artistic beauty of figure skating, with a focus on the figure transformation and the swirling trajectories. There we have the pleasure on the art side. I'm going to talk about dynamics on a different scale. The dynamics our naked eyes cannot see directly. The dynamics can be both scientifically interesting and practically useful. I'm going to talk about two examples of systems. One is molecular colloids, micron-sized colloidal particles whose design is inspired by molecules like shown there. The other is nanoscale biomolecules, which is an entirely new and exciting topic from my postdoc. Both systems we concern motions in a liquid that can be described by Stokes-Einstein equation, and still those two systems, they have different length scales, so they enjoy different opportunities as well as challenges. For colloidal particles, they can be easily watched using optical microscope, so the challenge is more on how to encode an interesting and relevant dynamics from the beginning. For nanoscale biomolecules, we use transmission electron microscope. So transmission electron microscope has been long regarded as incompatible with dynamics in solution, but I'll tell you it's no longer so. So we will first start from molecular colloids. I like to work in areas where applications can come together with the beauty of fundamental science, so I don't have to choose. Colloidal particles are such a system. You can see they have various applications in different areas, with their functions highly determined by the structures they can form into. But for a long time, those colloidal particles used to be isotropic. So here, by isotropic, I mean they have a homogeneous surface chemistry, so their interparticle interaction depends only on their interparticle distance. So that's why they can only pack closely, for example, into a lattice, like shown here. Many great minds have been working on how to make their dynamics even more interesting, and this is a long, exhaustive list of names. The motivation behind is self-assembly, the spontaneous formation of functional materials out of simple building blocks. So I was more on the material chemistry side when I studied, so I just naturally thought about this self-assembly question as a synthesis question, like how atoms can form into molecules and how molecules can transform and react with each other in a way people were not able to emulate with colloidal particles before. So my goal there is to really to see if we can make molecular colloids, is to see if we can make colloidal particles chemically reactive, to see if we can make colloidal particles form into structures that have a beauty and a variety, just like all the natural molecules shown on the screen. But this molecular colloidal concept is not easy to implement, especially if you think about the features of atoms in a molecule. That means our colloidal building blocks need to have directional bonding. They need to have a really well-defined coordination number, which means how many particles can surround a central particle. We need to have a lot of them, and they need to be dynamic. Traditional isotropic colloidal particles don't have all the features, and that is when our non-conventional colloidal particles, the Janus particles, come into play. So like showing there in this photo, a Janus particle has two phases of surface chemistries, so their interparticle interaction depends not only on their relative distance, but also on their relative orientation. So that's how we can have directional bonding. we can always fine-tune the size and the shape of the attractive side or the attractive patch of the Janus particle so as to control its coordination number. We can make a lot of them, and those particles at micrometer in size, they can be agitated by thermal fluctuation in solution. They're dynamic, and we can see their dynamics using optical microscope in situ. When there are more than one colloidal particle existing in the same colloidal system, the particles are no longer isolated. Instead, they will start to talk with each other. In other words, they will behave with the sense that there are other particles surrounding them. So we refer to those behavior as collective behavior. It's by nature quite complicated, but at the same time essential for the construction of higher order functional materials. So that's why I will focus on the dynamics when I implement the molecular colloids concept. The first experiment I did was to use Janus colloidal particles to demonstrate the coordination number concept. I made my Janus particles by starting from a monolayer of isotropic particles, have them directionally coated with gold, and then etch away the gold. So in this method, I was able to control the size of the gold patch really accurately such that only 3 nearest neighbors are allowed. And in this particular case, the gold patch is coated with alkoxanthiles, so it's hydrophobic, and the other side is charged. So when we disperse those Janus particles in water, the hydrophobic side will become attractive with each other, with the other side repulsive. We can always fine-tune the self-assembly dynamics by changing the salt concentration or effectively the kinetic strength in the system. The effect of this well-controlled coordination number is obvious, as you can see from this fluorescence optical microscopy movie. So here, each green sphere is one of our fluorescently labeled Janus particles. You can see they all self-assemble into this rather monodispersed tetrahedron shape, which was not possible before using conventional isotropic colloidal particles. And here I'm showing you a movie rather than a static image is because a tetramer is a 3-dimensional shape, so we can only determine its 3D configuration with confidence after we fully follow its rotation. So I was happy this coordination number concept worked, but then I became bored because there was no surprise. That's why I went ahead and increased the size of the attractive patch, so now we have a half-half geometry Janus particle. And when we did the self-assembly, now we can see a distribution of small clusters like shown there in the table. This table may look quite complicated to you at first sight, but really what is showing there is for a given cluster size, the clusters would always adopt the shape that can have the maximized number of attractive contacts so as to lower its enthalpy. When there are more than one configuration that can have the same maximized number of attractive contacts, we will have colloidal isomers, just like molecular isomers since they have the same composition but different configurations. As a chemist by training, I simply couldn't resist thinking about this isomerization reaction. It looks so neat in the formula. In terms of isomer time in equilibrium, it will be highly dependent on their relative free energy levels. In this particular case, the octahedron can eventually win over since they enjoy greater rotational entropy. As to the kinetics, here I was able to go beyond the molecular reaction analogs since now the isomerization reaction happens on a time scale and on a nanoscale that is visible to us. So like shown here in this movie, you can see the two particles of the corner of the bipyramid can just slide together into the center to form into an octahedron. So that's how we can really tell the reaction pathway one particle at a time without averaging. And I can only see this one single reaction pathway for all the isomerization reaction in the system. So to me, this really means this might be just a simple elementary reaction without fancy intermediates. And again, to me, that means we should be able to just use one reaction constant to describe this isomerization reaction. So does it really mean we can really use molecular reaction kinetics to quantify our colloidal dynamics? It didn't take me long to realize this was a challenge on its own, because our isomers, they are not alone. They're in this reaction soup, a really crowded one, with all the other clusters that can transform into them or from them. You can see from this reaction network. And this reaction network, as nice as it is not conceptual or imaginary. It's actually for my manual tracking of all the cluster interconversion events in movies. So behind these 20 reaction pathways is more than 100 clusters. As you can imagine, this manual tracking process was quite time-consuming. But it was also during this time-consuming process I realized eventually we only have 3 reaction mechanisms out of all the reaction pathways. So monomer addition, the addition of a single particle onto a pre-existing cluster to grow into a larger one. Cluster fusion, the fusion of 2 small clusters into a larger one. And isomerization. It's really just in the isomerization reaction it will require both a change in the particle relative orientation, but also a change in the relative positions like I showed you in the earlier movie. So to me, this really means the isomerization reaction will continue happening even after all the other reactions in the reaction network reach equilibrium. And to me, this really means this separation in the reaction timescales can help us decouple the isomerization reaction from all the other reactions in the reaction network. So I went back to the movies and checked the number of isomers with time. And indeed, the number of isomers will continue changing even after the number of all the other small clusters became stabilized. We can fit this change with a single exponential decay, which agrees with our simple kinetics picture. So I was satisfied by now because I was able to use molecular reaction kinetics to describe our colloidal dynamics, although they are 4 orders of magnitude different in size. But I also know there will be always someone in the audience wondering, oh yes, you show us your colloidal particles are chemically reactive, so what? One significance is now we can predict the products or the materials we can get. So here we define a reactivity term, which means how easy it is for one particle to form a new bond with an incoming particle. With that definition, let's take a look at the pentamer. The particles at the end of the pentamer can rotate much more than the particles in the middle, which means the particles at the end are more reactive. And that agrees with my earlier observation, where we can always see an elongated growth as the cluster size becomes larger. And now, let's push this trend further, and guess what you will see? Helical chains, actually triple helical chains, like 3 strands go twisted with each other. You may start to think about other helical chains in biological systems, but here, our helical chain is predicted by a simple geometry or kinetics argument. The building blocks we use, the Janus particles, they are not chiral at all. Another interesting thing here is for the particles within the helical chain, it always has 6 nearest neighbors, which is the maximized coordination number for half-half geometry Janus particle. So that means the helical chain is not only the structure that is kinetically favored, it's also the structure with the lowest enthalpy. So in my experiments, I pursued the prediction by making my Janus particles more approachable with each other so their self-assemblies can grow larger. There are examples when predictions don't come out in reality, but this time it worked. As you can see from this movie, we have 2 helical chains, the 2 helical chains of different handedness. And that is because a helical chain with different handedness has the same free energy levels. Those 2 helical chains are trying to hold hands with each other, and once they're hands in hands with each other, they start to relax. In this particular case, they're holding hands through the kink, and the kink can eventually get annealed out due to the thermal fluctuation of the particles. So this is a story about Janus particles, and the story traveled really fast. First, the Dow Chemical Company came to us when I was still a graduate student, offering us $300K per year guarantee for 5 years for us to work on some applications I'm not really allowed to talk openly today. And then later, DuPont, one of its major competitors, also approached us with a similar offer for us to study on some applications on using the particles to make people appear drier from shower. So I should say our initial focus on the kinetics and also the thermodynamics of our Janus colloidal particle self-assembly just naturally branched out to applications we didn't expect at the beginning. And that's our unique strength. I taught polymer engineering in my PhD, so I know the field of polymer engineering has been revolutionized by the use of diblock copolymers. So there, the two segments of the polymers can really give them a much richer phase diagram of the structures they can form into, just like our Janus colloidal particles. But polymer engineers, they didn't stop at diblock copolymers. Instead, they proceeded with triblock copolymers. So the question to me was, can I also learn from them to push my Janus colloidal particles further? That's how I got this idea of triblock colloidal particles, like shown here, with 3 separate domains of functionalities. The making of such triblock colloidal particles was a challenge on its own, was a project on its own. So eventually, I was able to make highly monodispersed triblock colloidal particles with a really well-defined coordination number. You can imagine if the coordination number equaling to 1, you can see single particle chains like shown there. Interesting but not surprising. I'm not going to talk you about this. I'm going to talk about what was missed in earlier computer simulations, not to mention in earlier experiments, a case when the coordination number equaling to 2. You can start to draw on your scratch paper because this is really a tessellation problem, like how bonds can extend in 2 dimensions and how regular shapes can really tile on a planar substrate. And I'm going to show you the result using my experimental movie. They can form into a Kagome lattice. Really beyond the name, the significance is it's an open lattice. It's a lattice with large hexagonal pores. It's a lattice that is not closely packed. It's a lattice that a lot of people can think about when they relate to the traditional engineering of colloidal structures. You can see how ordered and crystalline the lattice is from the fast Fourier transform on the right corner. You may be able to identify 1 or 2 defects in the structure. That is because for the formation of a perfect lattice that required the perfect positioning and also the alignment of every particle at the lattice side, which is not easy. So the defects are tolerated by entropy effects or possibly also by kinetic traps. This is a new structure. This was the first time people were able to make such open colloidal lattice out of solution phase self-assembly. And this new structure really invites new views. You can see it as a porous filter with 2 populations of pores, not only different in the size and also different in the pore surface chemistry. You can even see analogs with protein molecules. So the crystallization kinetics here is a 2-step process which has been reported before in protein crystallization. And we regard it as more than a coincidence because the protein molecules studied also have a patchy surface, just like our artificial patchy colloidal particles. Of course, an interesting result always have a story behind. So the first image I got for the self-assembly was not this perfect. You can see from this image, we have single particle chains, we have irregular networks, basically a structure overwhelmed with defects. Of course, you can think about ways to really anneal the defects one by one, but I want to be more efficient with my time. So here comes the trick. It all depends on the attraction strengths between the attractive patches. They need to be strong enough so as to bias the self-assembly towards the structure of the lowest enthalpy. At the same time, they need to be weak enough to allow self-correction of misaligned bonds. So with that trick in mind, I checked the evolution of structures with time. And here, the red lines really highlights the nearest labels. The blue lines together with the blue circles highlights the particles with the red Kagome ordering. At the beginning, the red area dominates. Essentially, we have irregular networks. But as time goes by, the particles are agitated by thermal fluctuation in the solution, and they start to self-correct. Until all the particles, they can form into a crystalline domain of the Kagome lattice like shown there. So that's the power of self-correction. If you are more patient, say waiting for 1 or 2 days, you can get a large crystalline domain like I showed you earlier in the movie. As I mentioned, this is a new structure, and this structure obviously has a beauty in appearance, but I also want to find its scientific beauty inside. So finally, that happened when I ran into a condensed matter theorist, Xiaoming, in a conference. She didn't know anything about colloidal particles, but she quickly recognized the Kagome lattice. It turns out the Kagome lattice belongs to a special family of isostatic lattice in the condensed matter theory. So that means if the lattice is composed of isotropic particles, the lattice can freely deform without paying any energy penalty. Geometrically, we can always see the Kagome lattice as a tile of small triangles, and the small triangles can freely rotate without breaking any bonds. In other words, a Kagome lattice is not stable. But from the movies I just showed you, our Kagome lattice, although with the particles fluctuating or vibrating at the lattice side, is stable. So this puzzle really brought Xiaoming and me together to think about what is new and different with our patchy colloidal particles. What's the new thing we can contribute to this rather classical lattice dynamic theory? It took us a lot of phone calls and emails to realize eventually our patchy colloidal particles can contribute a new term of rotational entropy to the effective Hamiltonian of the lattice. So like showing here on the left corner, for our patchy particles at the lattice side, now they can only rotate to a certain degree without breaking any bonds. And this change in the rotational freedom can really lift up the energy barrier against the lattice deformation. So to quantify this effect, I'm showing you part of the phonon structures of the lattice. If you are familiar with condensed matter physics, you will recognize this shows the square root of energy of different modes at different positions in the reciprocal space. But if you are not familiar with condensed matter physics, no worries. You can always see it as hybridized molecular orbitals. But instead of showing the energy of electrons, you are seeing the energy of phonons, vibrations. For the lattice that is composed of isotropic particles showing on the left, you can see this one energy mode with zero energy, which means there's no energy barrier against lattice deformation. That's why Kagome lattice was traditionally regarded as not stable. But if you look at the phonon spectrum for the lattice made out of our tripolar particles, you can see now that mode has been lifted up. And now we have energy barrier to stabilize our Kagome lattice. In retrospect, it's interesting because it's a rotational entropy term. We should favor this order that can really stabilize our ordered crystalline lattice. In other words, we have order from disorder. Another thing I want to highlight here is those tiny little squares. Those are actually my experimental data. So in experiments, I was able to track and measure the vibrations of particles at the lattice side and then back calculate the phonon modes. It agrees really well with the theory. So some of you may recall for normal crystals, we can measure the phonon modes using neutron scattering. And here, on a different scale, we're measuring the phonon modes using optical microscope. You may think the stability of this Kagome lattice is the end of story, but keep in mind, a Kagome lattice is an open lattice with large hexagonal pores, so it actually has some free space. That's why when I apply a lateral pressure along the lattice direction, now we can see a new lattice form, which is the hexagonal lattice showing on the right. This is a new lattice. This is a new face of the lattice on the far end of phase space. You may see polymorphism here, and I'd like to offer you another perspective. We are able to make two stable lattices from different conditions from the same building block. That means now we have a responsive material. The porous film can just collapse into the closely packed film with its pore size and hydrophobic hydrophilic patterns totally tunable. And you can switch the film in these two configurations back and forth with application or the removal of the lateral pressure. So far, we have the colloidal particles involved on their own without interference of their dynamics. Of course, we can do more. So here, I'm showing you one example where we applied electric field. You can see the particles are more agitated because now they can utilize external energy. Along the way, we studied by building up self-assemblies using the knowledge of how atoms can form into molecules. We watched the self-assembly dynamics. We watched the structural transformational dynamics of self-assemblies as a material and also as a model system for us to solve puzzles in theory. And all of those efforts were enabled by our capability to really see the dynamics in situ using optical microscope. But this simple seeing is believing principle is not always this convenient. When I want to zoom in to really learn the nanoscale dynamics of our initial inspirations, the molecules, I came to realize a different kind of challenge or a different kind of opportunity. So here, I'm particularly interested in the biomolecules because I want to learn from living systems on how to make our artificial colloidal systems smarter and more multifunctional. Of course, I also learned from my biophysics readings that the 3D dynamics of biomolecules has its own well-recognized motivation. It's all well said in this video published on YouTube a while ago. We want to understand the living functions of living systems to engineer drugs, to treat diseases, which is usually determined by the biomolecular transformational change. But this video is just animation. It's not real experimental data. That's because to really see the 3D dynamics of biomolecules, it requires an imaging tool that can really resolve nanoscale dynamics, which is a challenge that is holding back the field for a long time. Our old friend optical microscope has a spatial resolution of hundreds of nanometers as determined by the diffraction limit, much larger than most biomolecules. The super-resolution optical microscope can really increase the spatial resolution to tens of nanometers, but it achieves so by sacrificing its temporal resolution, not to mention it can only resolve location, not the morphology details at the nanometer scale. That's how we have this third option, transmission electron microscope, or TEM. TEM works like an optical microscope, but instead of shining light onto the sample, we shine electron beam. It can give us really high spatial resolution. As you can tell from here, a series of TEM images, you can see the shape and also the morphology of the DNA origami structure really well. But keep in mind, TEM works at a high vacuum. So that means even if you are allowed to insert a liquid sample into the TEM, the sample will be dried out and leaving you no dynamics at all. That's why when I read this one paper published in 2012, I immediately know what's the new field to explore. So in this paper published in my postdoc lab, the graphene liquid cell technique was demonstrated for the first time. It's essentially a tiny holder that can really contain liquid against high vacuum. Its configuration is like shown here, with two graphene layers sandwiching a liquid sample in between. The graphene is impermeable to liquid, so it can really stop the liquid from evaporating into high vacuum. We can have strong van der Waals force between the two graphene layers so to seal our liquid pocket really well. Additionally, graphene is electron transparent and it can give us a really thin sample, so we can still enjoy the high spatial resolution TEM despite all the liquid molecules surrounding our sample. The power of this graphene crystal was first demonstrated to me in the first experiment I was involved. The system is simple. A plated nanocrystal in an organic solvent, and the nanocrystals can move and rotate due to thermal fluctuation. So in the movie I'm showing here, on the left is the TEM images we got. We corrected the central mass position of the nanocrystal so you can focus on its rotation. You can see lattice fringes in a liquid environment, which was not possible before. You can see the nanocrystal is truly rotating from the change in the fast Fourier transform pattern. So you can imagine, if we can really watch this rotating nanocrystal continuously for a long enough time, then eventually we will be able to capture all the different facets of the same nanocrystal, and then back calculate its three-dimensional atomic arrangements. So here, with this new technique, even a simple system can try to answer one important question in nanoscience: the positions of atoms, or potentially the positions of dopants or defects in a nanocrystal. So I was amazed at how powerful this tool is to resolve nanoscale dynamics. But biomolecules are much more trickier when it comes to TEM images than nanocrystals. Biomolecules are usually in an aqueous buffer solution, much more evaporative than the organic solvent we used earlier. We want to see the 3D dynamics of biomolecules, which means we want to minimize the interaction between the sample and our substrate. So for these two requirements, I did a quick check. I optimized the sample preparation procedure using the gold nanocrystals moving in an aqueous solution, and then I observed them at the TEM. The gold nanoparticles are moving, which means, yes, we are able to trap aqueous solution between two graphene layers. And they are moving following a simple Brownian motion, a simple one, with just one diffusion coefficient, which means there's no localized attraction between the sample and our substrate. So these two requirements are met. Biomolecules are usually sensitive to electron beam damage, but how sensitive they are in this particular configuration of graphene crystal is not known. So I was able to try with the first experiment. Biomolecules are usually composed of low atomic weight elements, which shows little contrast in TEM. That's why, in my proof of concept experiment, instead of imaging a biomolecule directly, I image a nanoconjugate, a dimer like shown there, with two gold nanoparticles bridged by a double-strand DNA. The length of the double-strand DNA is much shorter than its persistent length, so we can regard it as a rigid rod. This is a nanoconjugate of relevance because it has really nice plasmonic coupling properties, but with its real 3D configuration solution not easily resolved before. And for the purpose of imaging, the gold nanoparticles can serve as a marker for the otherwise invisible double-strand DNA. So I'm going to show you a series of TM images I got, and I have more TM images than those to really tell me we do have two gold nanoparticles moving together as a dimer. And then let's look at the images. You can see two dark circular shapes. Those are the projections of the gold nanoparticles. You can see the distance between the projections is changing. At one moment, the two projections even get overlap with each other and then become separated again. And that can be only possible if we have two particles rotating as a dimer in 3 dimensions. So we do have motion in 3 dimensions. And now here comes the moment of truth. Is DNA really able to hold the nanoparticles during the whole imaging time up to minutes? I'm going to show you 3 data sets. One is trajectories, the positions of gold nanoparticles, the projected positions of gold nanoparticles with time. You can see 3 kinds of them, the single particles and then dimers bridged by different DNA lengths. The difference is obvious. For the dimers, you can always see 2 trajectories roughly parallel with each other with a distance that is tunable by the DNA bridge length, with a distance that is much smaller than the diffusion length of a free single nanoparticle. We can look more closely into the projected interparticle distance. The projected interparticle distance is fluctuating because our dimers are rotating, But still, the maximum of the projected interparticle distance of a shorter dimer is half as much as that for the longer dimer, which is consistent with our DNA design. Finally, we can look into the correlations of the trajectories. So for two gold nanoparticles in a dimer, their motion is highly correlated with a correlation coefficient close to 1. But for our control, if we look at two randomly choosing single nanocrystals, their correlation coefficient sometimes can even go to negative, which means there's nothing holding them in between. So I'm really going out of my way to really show you these three data sets because altogether they show an interesting, also surprising fact. The DNA is able to hold our gold nanoparticles together during the whole imaging time. And this is a surprise because for the conventional TM imaging condition, the DNA will be damaged by now. The amount of our sample is too small for us to really check if the DNA molecules are still viable after imaging. Meanwhile, more and more colleagues are doing relevant yet independent experiments showing the graphene can really lower the electron beam damage to the sample. So that can be one possible reason. At this moment, we just appreciate the opportunity to really use this technique to image a sample continuously in liquid environment, to image a sample including a biomolecule. I promise you 3D dynamics. And the 3D dynamics of dimer can be too obvious to be interesting. That's why here we have a trimer with 3 gold nanoparticles bridged by 2 double strands of DNA. Then in this case, for each TM image, we can measure 2 projected interparticle distance, D1 and D2. We can always assume a real interparticle distance, L1 and L2. Then for each TM image, we can just back calculate the 3D coordinates of the trimer. We can do the same for every TM image in continuous TM movie so as to obtain the configuration and the motion of the trimer in 3 dimensions. So I'm going to show you the result in this movie. On the left is our TEM. On the right is my calculation. And the red arrow really highlights the orientation of the trimer in 3 dimensions. You can see the TM image agrees really well with my calculated projections, which again shows us we do have a rigid trimer throughout the whole imaging time. And this was the first time people were able to use a series of 2-dimensional projections to do such 3D structural analysis and 3D motion tracking. A side note here is such 3D analysis was not possible before using conventional TEM, because in a conventional TEM, even if you start from a 3D structure, the structure can get flattened and collapsed during the sample preparation, leaving you no 3D information at all. So I enjoyed the image of a 3D rigid shape for a while, and of course came to realize the more interesting thing would be to really image a conformational change in real time and in situ. I learned from my friends in biology that the aptamer, a special kind of DNA, can interact with a protein molecule in the many different ways listed here. And all of those non-covalent interactions can potentially change the configuration of an aptamer. So the question I have is, can we really use the aptamer as the linker for our dimer instead? So we can really watch the transformational dynamics of the aptamer, again from the motions of the gold nanoparticles as a marker using TEM. Moreover, going beyond the purpose for imaging, if there is a change in the aptamer configuration when it's exposed to a protein molecule, can we really use this change to sense the presence of protein molecule at a really high spatial resolution, at a single molecule resolution? That's why I don't want to miss the chance to engineer a sensor, and that's why I choose this matrix metalloproteinase as a protein. So this is an interesting protein in cellular growth because it can really eat up the extracellular matrix. And it's really important for cancer research because in cancer cells, they usually have a high expressed level of such protein. But this protein is just simply hard to be detected using the conventional biochemistry technique, since this protein has a family of structural analogs. And that's why, in my design, I optimize an aptamer sequence that can only bind to this protein highly specifically using this evolutionary column. So that's how we can get our aptamer sequence. And with that aptamer sequence, I enjoy the pleasure to learn a series of new techniques before I can make the dimer, because no one has really used this particular kind of aptamer before in the nanoconjugates. So this is a new structure. I know from the binding assay that the aptamer can bind with the proteinase at the nanomolar concentration, but that this binding event really involves a change in the aptamer configuration. Does it really involve a change in the interparticle distance of a dimer, some change that we can actually see under TEM? So that was a question I have in mind. And here comes the merits of using gold nanocrystals. The gold nanocrystals, they can have connective electron motions upon the exposure of light. So that means when these two gold nanoparticles are this close with each other, with a distance smaller than their size, they will start to talk with each other and change their plasmonic resonance peak positions. So in other words, there's peak position of the scattering spectrum, which we can really measure from dark field image, is highly dependent on the interparticle distance. So here, I'm showing you two dark field optical images of living cells saturating or not saturating this protein. And the substrate is covered with our dimers. You can see the color of the scattered spots, our dimers, are different, which means, yes, there is a difference in terms of peak positions of scattering spectrum of the dimers, which again means, yes, there is a change in the interparticle distance in the dimer when it's exposed to the protein molecule. And this system is already quite interesting on its own because essentially it's a highly specific sensor that can really sense the presence of this protein molecule at a high spatial resolution, highly specifically. And to me, this system is also the second model system for us to really see if this binding event can also happen under the electron beam environment of TEM, to see if we can really watch this aptamer transformational dynamics using the gold nanoparticles as a marker using our graphene crystal TEM. Eventually, my grand goal is to get rid of the gold nanoparticle markers to see the biomolecular conformational change directly. I have more ideas as to how to increase the electron beam tolerance and how to increase the image contrast. More experiments are currently in progress. So with that, I hope I show you how dynamics can help us design artificial systems and to help us understand living systems. I'd like to thank both two groups I worked with. As you can see from the photos, both two groups resemble each other by having really encouraging advisors and by having really happy group members. So that's what I'm looking for in my own lab. I'd like to thank the Miller Institute for generously providing me money to do independent research so I can just try with risky ideas. Thank you for your attention.